next we look at the envelope extraction. So, here we have taken an EMG signal. In case of EMG signal, we know that whenever we exert some actually force through the muscle, so they are excited and that gives rise to some signal and we get the noise like kind of actually pattern. And if we look at that one measure of the volation, that how much actually we are exerting, that could be given as the this envelope of the signal. Okay. So, that could give us a measure that how much actually effort we have given. Now, if we look at the EMG signal, the main components are within say 200 hertz, some components are there going up to 1000 hertz, but if we look at the envelope, the maximum frequency could be of 20 hertz. Okay. So, this is one situation we get. Let us look at one more such example, that here we have taken the PCG signal. In case of PCG signal, along with the R wave, what we get, the ventricles they are getting contracted with the QRS complex, and the bulb the blood which are accumulated in the ventricles, now they start coming out of the ventricle, they are getting into the arteries. So, there would be some noise or vibration created out of the turbulent motion and the valves are forced to actually open first for that. So, all these together, the opening of the valve, the rushing out of the blood out of the ventricle to the arteries causing the turbulence, they gives rise to this S1 wave. Okay. And after that, when actually the ventricles they are relaxing, then we have that the other wave, that is the ST wave, where the valves are actually getting closed because the ventricles are relaxing. So, at that point if the valves does not close, there could be a backflow. Okay. So, just to make sure there is no backflow, that this part, that there is a that closing. So, that gives rise to the signal S2. So, S1 and S2, these two are very important to know the health of the arteries at that point and whether the valves are properly closing or not. So, one measure that how much noise it is creating can again be the some kind of envelope of the signal, and again what we get compared to that the frequency of the S1 and S2 wave, these envelopes should be much more low frequency. So, how actually we can extract them for our purpose, that comes as a challenge. Okay. So, let us see that how this point was actually taken care. So, from the basic definition, that what it is done, that we have that first we should take care of the name, that who has proposed this, that Lehner and Rangayan in 87. So, what they suggested to make use of this the basic definition of envelope, which suggests we should take the absolute value of the signal, integrate it over the time and take the average to get actually the envelope. So, what is suggested, that we should take a MA filter for averaging, and to make it positive for the PCG signal, that we should take square Okay. So, we should take MA filter on the squared value of the our PCG signal. So, that was the suggestion proposed by the Lehner and Rangan. So, they told about a small MA filter which can accumulate the energy which is positive, because the purpose of taking the absolute value or the energy is the same, that because the signal is oscillatory, that if we do not force it to make positive, they will cancel, their contribution will cancel each other when we accumulate them. So, either we have to take the absolute value or we need to take the square, and Lehner and Rangan they took the strategy that we should take the square, and the weight actually they have taken, it is not the simple MA filter, they have taken a window which is a triangular window. Okay. So, the latest point, that n, the value would be maximum, and then it should actually go to 0. So, it would be having a tapered one, that means the most recent actually values or most recent points, they will contribute the most, and the one which are far in the past will contribute less. But contribution of multiple points are required to do the low pass filter. Without that, we will just get the contour of the signal itself. Okay. So, we do not want that, we want that envelope, and for that this strategy is needed. So, for the PCG signal under consideration, it was actually sampled at that you can say about 1 kilohertz, 1024 hertz, and they found that m equal to 32 is sufficient for that. Okay. So, with that Lehner and Rangan they proposed first to actually get the envelope and make use of that as an energy of the activity, or to measure that how much actually energy is present in S1 and S2. Now, let us proceed to see that what is the basic strategy here. First, we should have a rectifier here, because the signals are oscillatory. So, this rectifier it will take care of the fact that the signal becomes positive, and then we should have a filter. The filter is to take care of the ripple, that after the filtering we know whether we are doing that half wave filtering or full wave filtering, in either case that there would be ripple in the signal. So, we want to remove that ripple, and then that the low pass actually that filter, it will pass on only that the energy distribution what is changing with the time, that is the envelope we are looking at. And in this work, however, the choice of the filter is a trade off. What do we mean by that? That we want to get rid of the ripple, but at the same time we want to actually predict the envelope as fast as possible, that means as faithful as possible. Now, if we suppress all the high frequency terms, if we remove them very drastically, what will happen? The envelope will become flat, and when there is a change, especially in case of PCG signal, what we have seen that there is a burst of actually signal. Whenever S1 and S2 are coming, they are actually some burst of energy. For that, the envelope also is moving pretty fast, but if we allow all those components to capture that change. A part of the ripple signal also is actually creeping in, and that is riding on that envelope. So, that does not give us a actually good feeling. What we get, that the signal that is the envelope what we have extracted, that is actually corrupted. So, where would be that cutoff frequency of that low pass filter is a very crucial choice, and most of the cases you need to manually actually tweak that thing to get the best result. So, that is the challenge we are talking about in this case. So, people have explored actually more strategies. The first thing after this that comes in the mind, that is amplitude demodulation. We know that from the communication engineering how the amplitude demodulation can be done. If you have a signal that is in the form that observed signal is yt, which is nothing but that amplitude modulated signal, where st is the signal of interest and cos omega t is the carrier. In that case, if we are interested in the xt, which we are taking as the envelope, we need to remove the carrier signal. So, for that what we can do, first we go for the synchronous demodulation. In case of synchronous demodulation, what we are actually assuming, that we know that the carrier wave, the carrier frequency as well as the phase, that should be known in the receiver. So, as we know that, we can make use of that to demodulate the signal. Okay? Demodulating the signal, the purpose is to actually find out the xn from the yn. Yn is given, from there we need to find out the xn. So, for that what it is done, that by demodulation, that we have taken that demodulated value x d, the first part, that we multiply it, the observed signal or received signal y t with that same carrier frequency at the same phase. So, we get a term by replacing the y t, we get a term involving x t, and another term we get cos a square omega c t. So, now the cos a square term, it can be represented as that in terms of that the two parts involving one and other part is cos 2 omega c t. So, by that what we get, that out of this signal x d, we have two parts, one is at the baseline and another is modulated at twice the carrier frequency. Now, if we do the low pass filtering to remove this part, we are left with the scaled version of the demodulated signal or the signal of interest, that is x t, only a scaling has come. So, that is the way that we can actually get the demodulated signal using the synchronous demodulation. Now, that the low pass filtering again, that is a crucial choice, but what is actually interesting here, that here as the carrier frequency we are getting the twice of the carrier frequency, the gap between that modulated signal and the modulating signal, that gap has increased. So, that makes the job a little easy. However, here one crucial thing we need to keep in mind, we need to get very accurately that what is the carrier frequency and what is the phase of it. If we have some error in that, it can actually lead to the problem. So, that the people that instead of synchronous averaging, sometimes they look for the other one, which is called the asynchronous demodulation. And what is the example of asynchronous demodulation? The first approach that what we have taken, it can be taken as a part of asynchronous demodulation. Let us take some, say, sinusoid, just for the purpose of illustration, that if we have a sinusoid and if we take a actually half wave filtering, we would get the signals like this, that we will get the output in this way, and if it is say modulated, what we would try to get? We would try to get this line actually. So, for that purpose we do the low pass filtering, and then we would get here a drooping characteristics, we would get this kind of signal. So, the ultimate signal what we would recover would look like in this way. The more accurately we can actually remove these kinks or the ripples, it would actually give more and more accurate actually the envelope. Okay. So, that is what we call by our that what we call by our asynchronous demodulation. Okay. So, that is the other technique which can compete with the part, but in this case we need to either make it positive by filtering, or by adding a DC bias we can also do that. Okay. That if it is a positive signal, we can still do that and then try to remove that actually ripple out of that, and we can actually get the envelope in that way. Okay. Next is complex demodulation. In case of complex demodulation, that there is some assumption. First of all, let us take the case that all the signal, the spectra, they are not actually unimodal. So, we can have say multiple peaks like this, and in that case this may be idealized as that it has actually 3 bands of different central frequency and different bandwidth. Okay. So, if we take that in that way, then next thing we would like to know that what is the central frequency and what is the actually modulated wave that which gives this signal. Here we can start actually from the other point to get the understanding more clear, that if we take a sinusoid, what would be the frequency? It would be a actually impulse like that PSD it will give. Okay. It will be all the energy will be concentrated at a particular frequency. When we have a modulating signal with on this carrier, then what we will see, the PSD will actually be a peak taking that central frequency as the peak, and it will get a spread. So, here we can think of this complex signal as actually combination of such amplitude modulated signal. So, that is the basic idea in case of the complex demodulation, and in that case the idea is if the signal is constituted by couple of such signal which are amplitude modulated signal, let us try to find out those carrier frequency and that modulating signals. Okay, that will give us a description about the signal in a better way. So, what is the first task we do? We look at that for demodulation of that the amplitude and the phase characteristic of the signal for each frequency band of interest. Okay. And usually this frequency band is determined by the PSD, that we take actually each of the peak as one carrier, and so the trough actually gives the limit of that. So, we take as a band, and that kind of that each band we take one at a time, and we try to find out that what is the carrier frequency and the modulating signal in this case. So, for that purpose the signal is represented in this way. The signal x t, it is taken as that a modulated signal with the center frequency, that is the peak what we get in the PSD within this band, and it is modulated by a actually signal A t, and there is some starting phase of it also. And what happens to the rest of the part of the signal? That means the energy in the other band, that is taken as the x r. Okay. So, this is the form that at this moment we are not interested in the part x r, that serves as a, you can say that the remainder in this case, and we are just focusing into this part and try to process this part to find out what should be our A t and what should be our phi t. So, for that what it is done, we first do some kind of the mathematical operation to get it more clear. The cosine term, it can be expressed in terms of exponentials or a pair of exponentials with that frequency f 0 and minus f 0, and then that x r remains in the same way. So, with that this complex actually terms, that we can actually multiply it with exponential minus j omega 0 t. That means, now we are whatever the signal we got, we are multiplying it again with the one of the carrier frequency or negative of the carrier frequency, and that helps us to get actually the first term, that is the modulating signal and the corresponding phase of it, plus the term with the modulating signal and twice the modulating frequency, and x r is also getting modulated. So, what we get, that this signal is in baseband, that this part only, this is in the baseband, rest of it they are at higher frequency. So, now if we use a low pass filter, we can easily actually eliminate these parts and we can keep this part only. Out of that, the amplitude part of it will give us that the modulating signal, and angle would be given, will give us the phase. Okay. So, that is the way we get that after the low pass filtering we get something y 0, that is A t into exponential j phi t, and if we take the absolute value of y 0 t, that gives us the A t, So, modulating signal here, please keep in mind what is assumed, that it is positive all through. So, if your signal was really a oscillating signal where the values are going to be negative, you would get only the part which is actually positive, and the negative component it would be rectified and we will recover that part. So, if we have a chance to synthesize that signal, then we should make sure that AT should be positive all through. However, that may not be true in real life situation, then we should be satisfied with the rectified form of that modulating signal. And if it is a simple wave, that the phase instead of becoming the time varying one, it should be a constant, for a simple example. And by that actually, that in this operation we have found the result of one particular band. We got the modulating signal and the phase of a particular band. Now, once this part is removed, that whatever we had as XR having the related that remainder of the energy, it is containing actually that energy of the other bands. So, we should work on that XR. That means, after finding out the AT and phi t, we should remove this part, deduct that part from the signal and get that remainder part, and we should work on that part again in the same way to find out the other, that the modulating frequency and the corresponding phase, and we should keep on going in that way to find out that modulating signal for each of these band. So, this process need to be repeated till all the bands are actually covered. So, this method, this has found actually a good application for the heart rate variability and the arterial blood pressure measurement, okay, variability in the heart rate, and along with that how the arterial blood pressure it changes. Okay. So, there this signal is used, and this signal also has been used in other places like for speech synthesis and speech analysis. There are a series of papers by Furui and Sandhi which actually makes use of this principle, and they analyze as well as synthesize the speech with the help of complex AM FM signals. So, now let us proceed to get actually another technique, that is called envelogram. Envelogram, this is actually having a unique idea that they are doing the same thing from a different point of view. This is proposed by the scientist that Sarakady in 1976, and he has actually noticed that we can use of the analytic signal. Okay? We can use of that analytic signal for this purpose. The magnitude of the analytic signal we can take, and he proposed that use of it for the PCG, which we represented by xt, and for that the corresponding analytic signal yt, it can be represented by xt as the real part, and the Hilbert transform of the xt, which is represented by xht as that imaginary part. Now, what is the easiest way to find out that analytic signal? For any signal which is real, we know that spectrum would look like this. Spectrum would be symmetric, say it would be like this. Okay. here we should assume that both sides are symmetric, and in case of an analytic signal, however, this part actually we can erase it. For analytic signal, the negative part of the that frequency, it does not have any energy. Okay. So, the corresponding signal in time domain, it would be a complex signal always, and the magnitude of that actually we can make use of it as the envelope. Okay. So, that what we have to do for that, to get that, we need to find out first the Hilbert transform. So, Hilbert transform we can get actually by convolving the signal with 1 by pi t. Okay. That is the direct way of getting the Hilbert transform. So, we can actually get that Hilbert transform in this way, but having a that integration like this, especially when the x t is not known, that it does not have any closed form, and numerically solving it is not also an easy task. So, we look for a better way of doing that, and for that we look at the frequency domain transform. That frequency transform of this signal, that 1 by pi t, it comes in a nice form, that it comes as minus j sine of omega. And what is sine of omega? It would be negative for negative frequency, positive for positive frequency, and both the sides the magnitude is 1, and it should be 0 at actually value 0. So, if we take the axis, so it is like this, that it is negative, then having a transition at 0, and then it is going to actually positive at that point, at the positive value. Okay. So, that is a actually known form, and we can make use of that to get actually that effect of it. We know that we have to compute the Hilbert transform, and if we look at the resultant signal of the analytic signal, we can make use of this Fourier transform. The convolution becomes multiplication in the frequency domain. So, the Hilbert transform part would be in the frequency domain would be x omega into sine of actually that j omega. So, with that, and another part, the real part will again contribute that x omega. So, we get that the analytic signal in this y omega in this way. Okay. We get this form. So, using that we can very easily find out the value, and here one thing we can note, that if we take this term 1 plus sine omega, the negative side of the frequency, that the values would be 0 for this term, for the 0 it would be 1, and positive side it will become 2. So, it is a one sided function of omega irrespective of the spectrum of x omega. So, in this way we compute actually the analytic signal, and here we go through the steps of it. The first part or the first step is we compute the discrete Fourier transform of the PCG signal, because PCG signal is of our signal of interest. It can be any signal which we want to actually calculate the envelope. for the negative frequency part, we need to force them to 0. So, for that what we do, that x k, that is the DFT part, we force to 0 for the coefficients which are between n by 2 plus 2 to n. That means, if we have the term starting from say 0 to, or rather let us take 1 to n. So, half of it at this part we are taking, forcing it to 0, okay. And that way and that is the way actually MATLAB gives these negative sides, it comes here. So, that is the way it is done for that MATLAB. If you have a different routine that gives the negative actually indexes in a different way, we should do the appropriate changes for that. So, now let us look at the next part for the positive frequency x k, that from 2 to n by 2 plus 1. Okay. So, that part we should multiply it by 2. That means, the positive part of the spectrum we multiply by 2, and the DC term which is given by the first term x 1, that will remain unchanged. Okay. We would not like to change that, because we want to compute the analytic signal, and that is the definition demands it in that way. Now, whatever is remaining in the spectrum, that gives us the spectrum corresponding to the analytic signal, and if we take the inverse DFT, then we get actually that analytic signal, and from there we can easily get actually the resultant signal. The magnitude of that resultant signal gives us the envelope. Okay. So, that is what we are looking at, and this is the way that we get that our job done. That is the last part we have covered for the envelope detection. So, we stop here. Thank you.